Okay, so now I think we're ready to talk about the utility death spiral. So we're going to assume today that we're talking about a regulated monopoly utility like Duke Energy. So vertically integrated, a company that operates and owns generation, transmission, and retail distribution as one business. So let's review how retail prices for consumers are set. Remember, we use typically this traditional rate making formula that um, requires utilities to try to hit a desired level of revenues, and based on that desired level of revenues, then they're going to set retail electricity prices. So for Duke Energy, let's say that their target revenues are R, and that the amount of money they want to make by selling electricity needs to cover their total cost of service. So that would be fixed plus variable costs, and we will review what those are in just a second, plus profits for shareholders. And so the profits that shareholders can make are a percentage of the depreciated value of utilities infrastructure. So they're not actually making profits on the electricity they sell. They're making profits as a percentage of the amount of infrastructure that the utility owned, which sort of represents the shareholder's initial investment in the company. So we could describe V as the depreciated value of the utility's infrastructure, and little r as the rate of return or return on equity for utility shareholders. So remember, fixed costs, we can break up the variable C in that rate making formula into two different pieces. So C is equal to fixed plus variable cost. A utility's fixed costs, remember, are not dependent on how much generation it sells. So these would be costs that it has to pay every year that don't really change. And so it would be like fixed operations and maintenance costs, but the really big one would be annualized capital costs. In other words, the mortgage payment on all the stuff they built. Variable costs are costs that utilities experience that do change that proportionally with how much electricity that they sell. And so these would be fuel costs, so how much coal they need to buy or how much natural gas they need to buy in order to produce electricity, as well as variable operations and maintenance costs. So the cost structure of utilities, we've seen this before, looks, if we think about it like visualizing it as a pyramid, you could think about profits for shareholders at the very top, and variable costs underneath that, and the really big base of the triangle. So most of the costs that a utility experiences are fixed, right? So, and a lot of that, again, is tied up in the mortgage payments that utilities are making on all the infrastructure that they built using borrowed sums of money. So they need to recover all these costs, right? They have to sell electricity in order to recoup the fixed cost, variable cost, and to make some profits for shareholders. And they do that by selling electricity. And there are, in general, sort of two different types of charges that you would see on an electricity bill. There are fixed charges that we pay. And so from the customer's standpoint, this would be an amount of money you pay every month, no matter how much electricity you buy from the utility. So it's sort of like a connection fee. The other part of our bill is volumetric. So we're going to pay some amount of money per kilowatt hour that we use. So the more electricity that we use, the higher our volumetric charges are. And so these can be flat or time of use. So in general, when utilities are making their money back by selling electricity, there's two sources of revenue that come in. Some of it's coming in through those fixed charges, those connection fees that every customer has to pay no matter how much electricity they are using. And then there's some amount of money that's coming in through the volumetric sale of electricity. And what you'll notice here, if we sort of visualize the proportions of a utility's revenue in two different parts, volumetric and fixed, that it's kind of the opposite, actually, of what the cost structure of the utility is. In this case, most of the money that a utility makes comes from the volumetric sale of electricity as opposed to those fixed connection fees. So in other words, what we're saying is that a utility's annual revenues, most of their revenues come from the volumetric sales, which depend on demand. So the more demand a utility has, the more revenues it makes. And the less demand it has, the less revenues they experience. So we can actually calculate how much revenue a utility needs if they have certain costs and an expected rate of return for customers, and then we can translate that into both a fixed and volumetric rate for retail electricity customers. So let's assume here that this an example utility has fixed costs of $50 million per year. And they have annual variable costs of $35 million. Their infrastructure is worth $250 million, and their allowable rate of return for shareholders is 7%. So we can plug all of these numbers into this rate-making equation. So we want to calculate big R, which is the target revenues for this utility. C here is going to be fixed plus variable costs. So we said fixed costs are $50 million per year. Variable costs are $35 million per year. So C equals $85 million. V is the depreciated value of the utility's infrastructure. So we're saying that's $250 million. And little r is 7%. That's the rate of return or profit margin that shareholders are allowed to make based on their initial investment in infrastructure. So here we can calculate R as C plus V times R, little r, and that gives us target revenues of $102,500,000. So then we can also translate that into, in particular, a volumetric rate of electricity. So the question here is, what should the volumetric rate be if the utility has 1 million customers and charges them each $40 per year just to be connected to the grid? And then we're also going to say demand for electricity is 1 billion kilowatt hours. So they want to make $102 million, 500,000 in order to cover all their costs and make this regulated rate of return 7% for shareholders. So we know that we're going to charge customers $40 each just to be connected, and we have 1 million customers. So that gives us $40 million without really selling any electricity. So we can first subtract that $40 million, which is the fixed charge for customers, from the target revenues of $102,500,000, and that gives us some leftover amount that we need to make by volumetrically selling electricity, and that leftover amount is $62,500,000. So we can say demand for electricity is 1 billion kilowatt hours. So if we're looking for a dollar per kilowatt hour amount that we need to charge for electricity on a volumetric basis, we can say we want to capture that 62,500,000 by selling 1 billion kilowatt hours. And so we can divide 62,500,000 by 1 billion kilowatt hours. And what we get is 6.25 cents per kilowatt hour. So that would be the volumetric rate that this utility would need to sell electricity at in order to cover its costs and also make a rate of return for shareholders, presuming that they're charging also $40 for each customer just to be connected. So now we want to look at what happens when a utility customer installs a solar panel or energy efficiency measures. For example, let's say that demand from this utility permanently drops by 5%. We could say that that's due to customers installing rooftop solar. And first, we're going to assume that the price is not changed to reflect that. So let's see what happens to the utility's finances. So a permanent loss of demand would not change the utility's fixed costs. Remember, the utility's fixed costs are basically the mortgage payments that they're making on all the infrastructure. So they have to make those mortgage payments regardless of how much electricity they're selling. Now, annual variable costs would change, right? So let's say that if they lose 5% demand, that their variable costs also decrease by 5%. So we could say that the variable costs decrease from 35 million to 33.25 million, right? So total costs, C, is a little different now. We still have fixed cost of 50 million, but the variable costs are a little bit lower. And so total C equals 83,250,000, so a little bit lower. The infrastructure that the utility makes is the same. It's $250 million, and the targeted rate of return for customers is still the same as well, 7%. So, if the utility experiences a loss of demand of 5%, their target revenues actually change. The amount of money that they need to cover their costs and meet profit targets for shareholders is a little bit lower, right? So, we can recalculate big R as R equals this new value of C, 83,250,000. Plus 250 million times 0.07. And that gives us a little bit lower number, 100,750,000, right? So that's how much revenues the same utility needs to make now in order to cover costs and meet profit targets for shareholders. So then we can figure out what actual revenues they would make, right? So again, we're assuming that they're not changing the price of electricity, right? So they're no longer selling 1 billion kilowatt hours of electricity because they lose 5% of their demand. So now they're actually selling 950 million kilowatt hours of electricity, and they're selling it at that volumetric rate that we calculated first of 6.25 cents per kilowatt hour, and they're still charging each one of their 1 million customers $40 per year just to be connected to the grid. So we're assuming here that even though customers are putting rooftop solar on their houses, they're not completely disconnecting from the grid. So the utility is still making that $40 million just by having 1 million customers connected. So the actual revenues they make is the amount of electricity they sell times the volumetric rate, plus all the money that they make from those connection fees. So that gives them 99,375,000, right? And so what you'll notice is that this is actually lower than their target revenues. What they needed to make was 100,750,000. So what we can do is figure out what the actual rate of return for shareholders would be, assuming that this utility experiences a loss in demand and doesn't change the price of electricity to reflect that. So what we can do is we can plug in our actual revenues in the equation as big R, and our actual costs, so fixed plus variable costs of 83,250,000, and then we still have the same infrastructure value of 250 million, but now we're solving for little r, assuming that we know what the actual revenues are. And so if we solve for r, what we get is 6.45%. And so remember, this is lower than what the utility was legally able to get, right? So the target was 7% for shareholders. And so what this is saying is that if a utility, lots of utility customers install solar panels or energy efficiency measures, that the decrease in revenues that the utility experiences is actually greater than the decrease in costs they experience, right? So it costs the utility less to provide electricity for its customers, but because most of the costs that utilities have are fixed, their revenues decrease more than their costs actually do. And so if they don't change the price of electricity, what that leads to is lower profits for shareholders. Now, what we do know in regulated monopolies is that utilities do legally have this ability to increase prices on customers in order to get this regulated 7% profit for shareholders, right? So utilities could increase the price of electricity on customers. And so this has happened in the past. And so think back to our discussion of the history of the electric power industry. So this has actually happened before in the context of utilities overbuilding nuclear power capacity. So utilities thought that electricity demand was going to increase more or less exponentially from the 1970s. And while in reality, electricity demand did continue to increase, it didn't increase as much as they thought. And so what happened is that they built too much infrastructure, and demand wasn't enough essentially to pay for that infrastructure. And so as a result, this lower than expected demand caused financial problems for utilities. And as a result, they increased prices, right? So they built all this stuff, and their mortgage payments were so high that when demand wasn't as high as they thought it was going to be, they were forced in some cases to raise prices on retail customers in order to pay for all the stuff that they built, but probably shouldn't have. And so this is one of the things that led to market deregulation in 2000s. It was part of why utility Utility commissions allowed, and the federal government allowed utilities to be deregulated and to introduce competition in wholesale markets for electricity. So, in a similar way, technologies today that reduce demand, for example, energy efficiency or distributed generation like rooftop solar, can force utilities to spread the same fixed costs that they experience that are associated with the mortgage payments from infrastructure, or over fewer and fewer individual units of electricity sold. And as a result, it's sort of the reverse of economies of scale, right? So you have increasing prices because you have um, the same fixed cost being spread out over fewer units. And so that means increased dollars per megawatt hour, dollars per kilowatt hour prices. So there are two possible results from this. And the first is cross subsidization. And the second is increased competitiveness of the distributed or disruptive technology. So let's look at each one of these. So when we talk about cross subsidization, we're talking about two things. The first is that adopters, which are the people that are actually putting solar on their houses, they're realizing lower energy bills. The whole point of putting rooftop solar on your house is if you would do that if you think you can save money, right? If it's cheaper to provide your own electricity than it is to go to the utility and buy electricity. Not everybody can do this, right? Because you might have to take out a loan to put solar on your house. Not everybody might want to do this. Some people might prefer to buy their electricity from a utility as opposed to be their own utility and be responsible for providing electricity to themselves. So the adopters, in theory, realize the lower electricity bills. At the same time, the non-adopters, so the people that stay in the utilities sort of customer pool, experience higher energy bills, right? Because if the utilities are experiencing lower profits because they're losing demand, right? In some cases, losing customers, and in response, they increase prices on the rest of the retail customers in order to make up for that loss of demand and loss of revenues. Then you have two different outcomes for two different pools of customers: the adopters, the people that put solar panels on their roof, realize lower electricity bills, and the people that don't put on solar panels on their roof experience higher electricity bills. So, what that also potentially leads to is increased competitiveness for the solar panels themselves. So, as energy costs for the non adopters increase, that pool of customers then becomes more likely to go out and buy solar panels, right? Because if the price of electricity is continuing to go up, maybe because people are buying solar panels, um, while for the cost of solar is decreasing, now you have another group of customers who might identify that putting solar panels on their roof is a way to save money. And so you have these two different factors happening at the same time. So this is just referring to the fact that as these lines, the levelized cost of electricity for solar decrease, and more people take or adopt solar, that might itself be part of what's driving those circles, the cost of electricity from utilities to go up, right? And so it starts to create this feedback loop where the declining cost of solar leads to increased adoption of solar. And the increased adoption of solar reduces utility revenues. And so, in response, utilities may have to increase electricity prices for non adopters. And as the prices for electricity for non adopters increase, they are themselves more likely to adopt solar. So, it starts this positive feedback loop.